Hello and welcome to my channel. I'll be discussing L'Hopital's rule today, and this is basically when you have to take a limit, right? So we all know what a limit looks like as x approaches a of f of x, and so it's just you're taking a limit, but not only that, this limit yields some indeterminate form. So something like 0 over 0 or infinity over infinity. I'll list them in indeterminate forms later on in this video. But when you get that, then use L'Hopital's rule, since substituting an a into this x value no longer actually gives you a limit. It doesn't actually work, because usually, when you have a limit as x approaches 5 for x squared, you know that limit's 25, because you can just substitute this a for that x. But now this is no longer the case, because you're getting an indeterminate form like 0 over 0 or infinity over infinity. Let's just rewrite those infinities. Alright, so let's just state what L'Hopital's rule is. So it says that if you have a limit of something, right, as x approaches a, of f of x over g of x, so whatever this f of x function is, it can be split into two different functions that are one over another. But we'll find that there are ways to manipulate regular looking functions into ones that resemble this kind of form, so you can use L'Hopital's rule to solve the limit. But anyways, let's continue with what the rule actually is. Equals, so you're just taking the limit of now the derivative, so f prime of x over g prime of x. And this is pretty much L'Hopital's rule, and the answer that you get here on this side will actually be the limit of that original thing. So there you have it. Alright, so let's just do a very quick, simple, easy starting example, right? No manipulations involved, just a simple sine x over x. So this is your f of x. And excuse me, and you want to take the limit of you want to find the limit as x approaches 0 of f of x. So you get that, right? And this very much resembles the form as I had showed you above, with two different functions, sine x and x, right here. So what we can do now is take a limit, but now take the derivative of the top and the derivative of the bottom separately. Again, we're not taking the derivative of the whole thing, we're taking the derivative of f of x and the derivative of g of x and doing this. So the derivative of sine x we know is cosine x, and the derivative of x is 1. And now we can substitute this a value into here, this 0 into here, and you get 1. So that the limit of sine x over x as x approaches 0 is 1. Now let's try another example, this time a bit more tricky, right? So let's just, at this point I'd like to list some indeterminate forms. So you have your basic 0 over 0 and infinity over infinity, and you always want the before you use L'Hopital's rule, you want it to be in either of these forms. 0 over 0, infinity over infinity, perfect for using for L'Hopital's rule. You have to do nothing more. However, there are other forms like infinity times 0 or infinity minus infinity. And for these two, there are more manipulations involved. So let's do one of these when you get infinity times 0 or infinity minus infinity. And there are also furthermore there are some more indeterminate forms that you should be cautious of, like 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. So if you see any of these are also indeterminate forms. But again, you should always, whether it's these three or these two, you should always try to get it in 0 over 0 or infinity over infinity to use L'Hopital's rule. So now that we know to recognize some more of these forms of indeterminate functions, let's try some more examples. So let's say we have the limit as x approaches infinity of x times sine 1 over x, right? And this we can clearly see is an infinity times 0. That's what this is, times 0. So we can just write that in there. And so this is one of our listed indeterminate forms, but now we have to get it to 0 over 0 and infinity over infinity. So how do we do that? Excuse me. So we can do that by substituting a value. So we can say let h equal 1 over x, and we can start substituting h in instead of x. So we can do that, and if we do that, you get the limit. If we get the limit with this h value substituted in, and instead of x approaching infinity, we now write h approaching 0, because if you put infinity here, you get 0. So again, we're just simply substituting everywhere there's an x, we put an h, and the h value. So 1 over h, so x actually becomes 1 over h, and you get sine of h. So the limit as h approaches 0, sine of h over h. So look, this is now, again, 0 over 0 form, and it's exactly the same as the problem we previously solved, the sine of x over x, and we know that this limit equals 1. So that's another simple way of doing it. And now let's do another example involving one of these three. So a basic rule for these two, when you see an infinity times 0 or an infinity minus infinity, you can generally say that you have to use that h method. So you have to h equal 1 over x. This is a generalization, but it works most of the time. So when you see these two, you should let h equal 1 over x. Now for these three, 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0, there's another nifty little trick we can use. So now let's do an example with one of those three. So let's say you have the limit of, as x approaches 0, of e to the x plus x to the power of 1 over x. So this, if we plug in 0 here, right, if we substitute in a, you get 1, right, anything to the power of 0 is 1, so e to the power of 0 is 1 plus 0, so it's 1, and then you have 1 over 0, which is infinity. So you have a 1 to the power of infinity. So again, it is one of our indeterminate forms, and we want to get it to either of these two. So how do we do that? Now in this case, we can define this, right? This is f of x is equal to e to the x plus x to the power of 1 over x. Now what if we took the natural log of both sides? Now that will solve quite a bit of things. It'll make this problem much simpler to deal with, and I'll show you why in a minute. So now what you can do, right? Because knowing our rules of logarithms, you can take this 1 over x and put it right here, right? Because this and that are the same thing. Is equal to the natural log of f of x. So now that you've written it this way, if you take the limit of this as x approaches, again, the same thing, as x approaches 0, you'll actually, and then reverse it, so let's just start. So instead of taking the limit of this to begin with, we're now going to take the limit of the natural log of the function as x approaches 0. So this is basically what we're doing. And if we write this as something we'll quickly recognize. So now if we look at it, you can see, right, this x, it's the same thing just written with the x over here on the bottom, and this is now a 0 over 0 form, because e to the power of 0 is 1 plus 0, the natural log of 1 is 0 over 0. So there you have it, you already have a 0 over 0 form. So now all you have to use is L'Hopital's rule. So we just take the derivative of the top and take the derivative of the bottom, and we should be golden from there. So let's just do that. And we'll have to use a bit of the chain rule here. So that's the derivative of that over 1. And let's not forget the limit, x approaches 0. And now if we do this, we get, let's see, so 1 over 1 plus 0 is 1, and then that's 1 plus 1, so it's 2, so 2 times 1 over 1 is 2. But it doesn't end there, because let's not forget, this is the limit as x approaches 0 of the natural log of f of x. What we need is a limit as x approaches 0 of f of x. So how do we find that? We just do what we always do. So if ln of f of x equals 2, that means f of x must equal e to the power of 2, right? We all know that because you're just taking e to the power on both sides, getting rid of the natural log. So we do the same thing here, and we just get rid of the natural log by doing what I just did there. So if the natural log of f of x equals 2, then the limit as x equals 0 f of x must equal e to the power of 2, so e squared. And that is actually our limit. So this brings me to another generalization that you can use. For these three, whenever you see 1 to the power of infinity, 0 over 0, infinity to the power of 0, chances are you can take the natural log of the function. So there you have it. Thanks for watching.